Section 1.62, we're going to look at an example on sequence and series. Is a fairly easy, straightforward one. Suppose in a sequence Sn, S1 is this particular expression, 2 over 1 times 1 over 1 squared. S2, you multiply it up to 4. See, when it's 2, when the number here down here is 2, then the subscript is 2, it means it goes up to 4. And then the stuff below goes up 1 less, and then each one, the numbers on the bottom are odd, numbers on top are even, and then it's the same number here, except that we will always square. So that's the pattern. And then S3, as you can see, now when it's the subscript 3, then you go up to 6, and the bottom go up by 1 less because it's the odd numbers, and then this will be the same number here as 3 squared. Now here, so we can see where the sequences looks like. So we're supposed to show that Sn is going to be less than 2 over n. Now if that is true, being that Sn are all positive numbers, and this thing goes to 0, then obviously Sn, the limit Sn goes to infinity, is going to be 0. So that's one thing we need to show. And the next thing we also want to show, even though this is not necessary once we show this, we already know that Sn goes to 0, but just for the fun of it, we're also supposed to show that Sn plus 1 is less than Sn, so there's a monotone sequence. Now, given that you can prove this, it doesn't matter if it's monotone. As long as this is less than that by the squeeze principle, it will go, the limit is already established as 0. So this is just something extra that we want to do for the fun of it. So let's write down the equation for this thing. So in general, Sn is equal to 2 times 4 times 6, etc. All going all the way up to what? 2n, okay? Because when it's 3, it will become 6. So generally it's 2n. And then the bottom, it goes 1 times 3 times 5. And it all goes up to 1 less the top. So it's 2n minus 1. And then this thing over here is times 1 over the same number as the subscript. So 1 over n to the power 2, because they're all squared, every single one. So that's our general equation. And now, okay, first thing we need to show is that this thing, no matter what n is going to be less than 2 over n. How are we going to do that? Well, you can do different things, but for example, we'll do some kind of a rearrangement. So we will move everything over, move the bottom over 1 spot, because 2 is over 1, 4 is over 3, and so on. So everything up here is bigger than what's down here, which is, but we want to show this thing going to 0, so we'll shove everything over. So we have 2 times 4 times 6, etc., going up to 2n. And what we're going to do is move everything over. Right now, 1 is under 2. But we're going to shove everything that way. So now 3 is under 2. So we have 3 here. Okay, 3 is under 2. 5 is under 4. 7 is under 6, etc. And then eventually we'll get up to 2n minus 1. But there's nothing under 2n. So what we're going to do is borrow the n from over here to be under 2n. So everything's still matched up. Times, then what we have left is okay, that's 2, 4, 6, 8. Where did 2 come from? Okay, now, anyway, so we go up to the 2n. So we go all the way up to 2n. Now this 2, I'm borrowing out of nowhere, so I'll add a 2 on top so they cancel out. So now I have constructed this thing such that I borrowed an n from here and also got a 2 on top. So what I have left here is 2 over n, because once I put one n here and put a 2 on top so that it balances out with the 2 on the bottom, so everything is lined up. Now, at this point, you look at this equation, what does that tell you? This thing, you see every fraction here is lined up perfectly, okay? And And each number here is less than what's on top. So each fraction is less than 1. Okay, 6/7, 4/5, etc. All the way up to 2n. Only the last one is exactly the same because it's 2n/2n, so it's exactly 1. But everything before is going to be less than 1. So this particular fraction right here, all multiplied together, is less than 1. So which means this whole thing is less than 2/n. That concludes our first proof that Sn is going to be less than 2/n. And this also shows that therefore the limit of Sn is going to be less than the limit of which is bigger than 0 because the terms are all positive, which is less than the limit of 2/n as n goes to infinity, and that would of course will just go to 0. So that we proved the second part, but we have some extra work to do. Not necessary, but slightly interesting. We have to show that this thing is less than that thing. To show that, we just have to go by the original definition and do this. We can do a fraction. That is, we can do Sn plus 1 over Sn. If this fraction we can prove that it's less than 1, then this inequality stands, because this inequality effectively says Sn plus 1 over Sn is less than 1. So here's what we are trying to prove. So to write down this inequality, we will write down first what is Sn plus 1. And so that is 2 times 4 times 6 going all the way up to 2n plus 2. Okay, because n turns into n plus 1. So 2n becomes 2n plus 2. And similarly, and the bottom is 1 times 3 times 5 all the way up to 2n plus 1. Because you have one more term. So the next term is 2n plus 1 times 1 over n plus 1 squared. Okay, and this whole thing is multiplied by, okay, big multiplication sign here, then Sn. Now for Sn, because it's dividing, we're going to flip the fraction around. So we're going to just copy this thing down, except we'll flip it around because we're dividing this, which is invert and multiply. So copy this down, 1, 3, whatever, 2n plus 1 minus 1. Okay, 2n minus 1, and then the bottom becomes 2, 4, etc. to n. I'm just copying this except shifting the top for bottom. Alright, so we have that much coming on. So that equal to, if you look at this goes all the way to, the 2 is on the top and this 2 is on the bottom. So this cancel out, this chunk of stuff cancel, this chunk of stuff out, and has left nothing but 2n plus 2 for just this piece. Okay, this piece and this piece cancels out. Similarly, this thing and this thing is identical except up to 2n plus 1. Everything else is canceled out. So it's 2n plus 1. And then next, we have the n squared. We'll just write that down. N squared from here. And then n plus 1, which is at the bottom. And then you have, okay, so there's 2n plus 1. So we have, we'll cancel out some of this stuff. We have then 2n squared divided by 2n plus 1 times n plus 1. Because we canceled out one of the n plus 1s in here. So we have only 2 left and this stuff left. Now at this point, you look at this, this is equal to 2n squared plus other 2n squared plus other stuff, okay, which this is 3n plus 2, plus 1, okay, 2n squared, 1 and 2 is 3, and then plus 1. This is going to be less than 1 because this is a fraction where n is positive and the top has this much stuff in it. The bottom has the identical things except a bit more. So this fraction has to be less than 1 no matter what n is, especially because n is positive. So that concludes our proof that, that this fraction here is less than 1. which means Sn plus 1 is less than Sn.